Ternary plots. How to plot points on a ternary or triangular graph. So ternary plots are used to plot systems with three components. And the sum of the three components always adds up to 100% of some quantity. Now these are typically found in material sciences where the three components represent proportions of a mixture or a compound. So for example, you can have a mixture that's 23% clay, 47% silt, and 30% sand. And now these plots are used to identify different phases and other intensive properties of the mixture that depend on the proportions, and these appear as regions on the plot. So why a ternary plot? Why not use a 3D Cartesian XYZ graph to plot points for these three component systems? We're more familiar with these types of graphs. Well, you can. And in fact, sometimes ternary plots are avoided entirely in favor of 2D Cartesian XY graphs. The third component is omitted since it can easily be deduced once two values are known, since of course they must sum up to 100%. And in fact, any system amenable to a ternary plot is also amenable to a Cartesian plot, but not vice versa. A Cartesian plot does not place any constraints on the sum of the three components. They don't have to add up to 100%. So they are free to take on any values regardless of their sum. So how do you plot a point? So let's consider a three-component system with components A, B, and C. And we're going to build our ternary graph paper. So let's start off. We label component A at one of the vertexes, and any point lying at that vertex represents 100% of component A in the mixture. So now what you do is you just imagine sending a wave out from A. So you have a 90% line, an 80% line, a 70% line, and so on, all the way down to the base opposite of the vertex of A. Now any point lying along the base represents 0% of quantity A in the mixture. So similarly for B, and similarly for C. And combining all three of them together, we have our ternary graph paper. So let's plot a point. Here I've selected the point ABC to be 29%, 46%, and 25%. So starting from A, we send a wave out from A down to the 29% line and identify that line. Then we move on to component B and we send a wave out from the vertex at B to the 46% line. And here we see they intersect. And in fact, that intersection does represent the point. And that's a reflection of the fact that the two components are all that you really need to uniquely identify the point. The third component is easily deduced by subtracting the sum of those first two from 100%. But we can just follow through to verify. So we send out a wave from the vertex at C to the 25% line. And lo and behold, it crosses right through where we expected it to. And there's our point. Now, a ternary plot can be used to graph trajectories of dynamical systems with three components. A trajectory is just a series of points on a graph representing the time evolution of the system. Now, these are systems that are kind of special because at all times during their evolution, the sum of the three components adds up to 100% of some conserved quantity like mass, or population, or energy, or money. So some examples of dynamical systems that are amenable to ternary plots. So we can consider something that represents a total population, and we can divide that total population up, say, into income tiers, into three equal income tiers. An upper income tier, a middle income tier, and a lower income tier. And you can see that we have different proportions of the population residing in each of the three tiers at any given time. So another type of total population relates to the spread of infectious diseases. So at any given time, you can have a proportion of the population that are susceptible to the infection, some that are infected, and some that have recovered. And in equilibrium pricing in three goods economies, you can have a total price that's constrained to always add up to $1 between three components. So you can have price of good A, the price of good B, or the price of good C. And in fact, we'll be looking at these three examples in some presentations to come. Now, there are some archetypal patterns when you're plotting dynamical systems in Cartesian coordinates and as well in triangular coordinates. One example is a periodic oscillation. So we want to see what that looks like on a triangular graph. So here we have three components, A, B, and C, and they're varying sinusoidally, so they're waving, and they're all out of phase. What would that look like in a ternary plot? Well, it would look a little bit like an ellipse. And notice at any given time during the evolution of the components of A, B, and C, their sum always adds up to 100%. So it's a very special system. You can also have decaying periodic oscillations. So this is similar to the first one, but in this case the amplitude is decreasing over time. And that looks like a little bit of a curlicue. So you have the same sort of ellipse, but it's now broken and spiraling down towards some fixed point. And last but not least, what would random points look like? So you can have A, B, and C varying randomly in time such that at any given time along the evolution, their sum always adds up to 100%, and that will look like exactly what you expect, a bunch of random points speckled throughout the area of the triangle.